Hi, my name is Ryan Booz. I'm a solutions engineer here at pganalyze, and today I'd like to begin our second conversation around pgstat statements, specifically what tracking unique normalized queries means when we're talking about the metrics inside of that in-memory hash table. Now, in the first episode, we talked about the in-memory hash table and some of the metrics that we track. In Postgres 18, there's about 45 columns. In earlier versions, there were fewer, and quite honestly, in newer versions, we're likely to get additional information tracked. Overall, this is still done, though, in that in-memory hash table. Now, the entries are unique by this key set: the role database, the query ID that was generated for the structure of the query or the hash, and whether or not the query was a top-level query. Now, I want to briefly talk about top-level, but I'll only do it on this slide. By default, pgstatstatements.track is set to top. And a top-level query is essentially the query that was initiated with a session or a transaction. So I execute select title from something. That's a top-level query. It's the thing I initiated. However, if that process, that query in turn, calls another query, that second query is not top level. It's not the one that I initiated with. And this is primarily functions and stored procedures. If I call a function, I'll get an entry in pgstat statements that might say select from function. If that function, however, calls other queries inside of it, if I have track set to top, I won't see the metrics for those internal queries. They are not top level. If I set pgstatstatements.track to all, I will then see those statements tracked inside of pgstat statements. However, the one nuance to understand is that there's no way to tie the execution of those internal statements back to the parent that actually called them. There's no column in pgstat statements that says, hey, these metrics are because of a function that called this SQL statement. There's just no way to correlate that currently as of Postgres 18, and quite honestly, nothing yet coming up in 19 or beyond. So let's look at this with an example of a pretty simple query. Select title from film with a where clause. Now, if I were to run that query on a database with 3 different users, I would get 3 different entries in pgstat statements. And let's say I'm hosting my client's databases. Each individual client gets their own database. Otherwise, it's the exact same structure. And as the application user, I run that query in each of those databases. Well, then I'll also get additional entries for each database. So in this quick example, I get 5 entries in pgstat statements. Now, if I simply change that select clause to title, rating, I end up with a new unique query, and therefore I now have 10 statements inside of pgstat statements for a pretty simple setup here. 3 databases on one server running with a couple different users, and I'm pretty quickly filling up pgstat statements. And that becomes one of the issues that I want to help you understand as we work through this series. pgstat statements does not track all statements for all time as long as the server is running. There's a maximum number of statements that it will track at any one time. And that, by default, is set to 5,000 statements. Now, you can configure this. You can make it higher. You can make it lower. But this is the upper limit of how many statements at any one time pgstat statements will be tracking metrics for in that in-memory hash table. Okay, so now we know that it's by database and role and this query ID, this uniqueness of the query. And if we're not careful, we tend to think, and I know I often tend to think, that the uniqueness of a query is simply based on its text. That's what we see. That's what I write. That's what my ORM is generating. But that's not it. It is structural. And so it takes that query, turns it into a structure, parses it, takes things out that don't matter, like constants or parameter values, and then it hashes that result. Now, this process is called jumbling, and I actually wanted to throw this in here because this is a term you will hear in the community. There's actually an internal function called JumbleQuery. It takes that query text, it walks the parsed tree that is generated from what that query represents, serializes some of the elements, replaces those constants, those parameter values, things of that nature, and what that ends up producing is what gets hashed and provides that query ID that gets stored inside of pgstat statements. And so a quick example would be something like this. I have the exact same query. I'm simply changing the where value, ID equals 1 or 2 or 3. Otherwise, it's the exact same query. It gets parsed, goes into JumbleQuery. The end result of that is hashed. and we end up with one entry in pgstat statements. I could run this 1,000 times with 1,000 different ID clauses, and I would still just get one entry in pgstat statements. Now, what does get normalized out of a query? The things that don't actually matter to the structure. Hopefully, most of this makes sense to you. Things like literals that could change over time, parameter values, whitespace and formatting, and even comments. Now, when it does come to comments, I do want to mention one thing, and honestly, even formatting to an extent. When you run the exact same query, but maybe you are injecting comments into the query text to track what functions in your application is sending that version of the query forward, the first execution of the query is the one that will get stored, the query text that we see. Remember, you can have many versions of a query with different comments in them, but if structurally they're exactly the same, you're only going to get one entry inside of pgstat statements. So just because you're injecting the comments doesn't mean you'll be able to search pgstat statements for those values later to find the execution of something from a specific function in your code. This is a really quick example to demonstrate that. I ran these two queries back to back immediately, and I got one entry in pgstat statements specifically for that first execution. The second execution happened, the metrics are stored here, but because it had already been parsed, it already had a query hash ID, and these are structurally the same otherwise, comments don't matter, I'm going to end up storing those metrics here. So again, if you are trying to inject comments as a way to later identify metrics to a particular process in pgstat statements, you might not be able to. The same thing pertains to SQLcommenter statements. I want to just briefly talk about this because these tags are often used by, again, ORMs to try and identify exactly where this SQL text came from. Now, these are comments just like the other slide, and so depending on how these are run, it may end up in pgstat statements, and quite honestly, depending on how it's executed, when you have comments prepended to the text, it might not even show up in here. I just wanted to call both of these things out because I see often customers and users try and go to pgstat statements, find an exact execution that's tied to maybe a span of their open telemetry data, and they think they should have a tag that matches, but they can't find it. Well, this is why. That version of that structurally similar query, the exact same query hash, was run after a different version ran first and stored its text internally. So keep that in mind. What does pertain to the structure of a query? What doesn't get normalized away? Well, it's things like the number of columns that are selected, the length of the elements in your in list, order by clauses, join structure, how many where conditions you have. The exact same query, it could be a really long, complex select query, lots of CTEs, and all that changes is the where conditions at the end. You're going to get multiple entries for each one of those executions. Now, one thing I wanted to call out specifically is the in clause issue. This is a problem with Postgres 17 and below, and I see it a lot with ORMs, and it's surprising to most people. And it can explode the number of unique queries tracked in pgstat statements very quickly if you're not aware of it. In Postgres 17 and below, if I simply have the exact same query, but where in 1, where in 1, 2, and so forth, every version of that in clause will produce a unique entry in pgstat statements. They are seen as structurally unique elements because of the way the parameters are set. Fortunately, Postgres 18 finally fixes this, and it will turn any where in clause into a where equals any in an array of elements. So where in 1, 2, 3 will produce the exact same query plan as where ID equals any in an array 1, 2, 3. And so we do this now by default in Postgres 18, which means we end up with one entry in pgstat statements. And really think about that. I've actually produced for some examples at times the exact same query, and I simply run it 100 times with 1 to 100 different elements. I end up with 100 entries in pgstat statements with Postgres 17 or below. This is a huge fix, and it really allows us to better track metrics in pgstat statements. So, to remind you, as we continue on in the series, what we're talking about with tracking pgstat statements is structural. It's not semantic. It's not what we think should be equivalent. Even if the execution plans would be exactly the same, it really comes down to, does the structural form of the query hash the same or not? For instance, we know logically, and Postgres produces the exact same query plan for the two queries on the left in blue. Film ID equals 557 is logically and semantically the exact same thing as 557 equals film ID. However, we'll get two unique entries in pgstat statements because they are structurally different. The same thing for the queries on the right, where in with multiple values is different from film ID equals any in multiple values. What pgstat statements cares about is structure, not semantically similar things. And so as we talked about at the beginning of this, the big issue for me and why this becomes something I want to continue to talk about with others is that maximum value. If you're not conscious and not aware of how quickly you can take up all of these slots in pgstat statements, you might be missing metrics for executions of things when you need it most. And that's because when Postgres reaches that max setting, when it's tracked, in this case, more than 5,000 queries, query 5001 needs a place for the metrics as it gets executed. And so Postgres deallocates some of the information out of memory, and now that information's gone until the next time you begin to execute those statements again. It really doesn't matter how big this gets. Ultimately, if you aren't aware of what's happening to generate these unique queries, then you're still going to fill up those spots if you're not handling this correctly. So the key takeaways from this specific episode, as you're thinking about what's being tracked, how we identify unique entries in pgstat statements, we are really concerned about high cardinality, which can cause us to lose information when we go to find it later. High cardinality comes from structural variation. ORMs love to generate lots of unique versions of a query just because of how you write it. Dynamic SQL that we're producing can create multiple unique entries when we didn't expect it. When you run many databases on one server, remember, pgstat statements is one in-memory hash table for the entire Postgres server, regardless of how many databases you have. And if you are connecting with many, many roles to do the same thing, you're going to end up with unique entries, even if you only have one or two databases. High cardinality drives that eviction behavior. And so now that we have looked at what pgstat statement is and what it isn't, in this episode, how we actually get these unique entries, next we want to talk about where the query text itself is actually stored. Quick hint, it's not in the in-memory hash table. And because of how it's currently stored in Postgres 18 and below, it actually has a bearing on how efficiently and effective you can track metrics in pgstat statements. So we'll look at that next in episode 3. I hope to see you there.